Okay. So should I start now?
Yes, you can start.
Okay, thank you. I have 1 hour including questions, no? So it would be more like 50 minutes or something like that.
Yeah, that's fine.
Okay. Okay, so thanks a lot for coming to my talk and for inviting me to give this talk. My name is Silvia, as Eleni said, and now I'm a postdoc at TUM. I just started. Before I was for 2 years at King's. But today I'm going to talk about something that I finished in 2022, 2023, together with my collaborators in Valencia. And yes, as Eleni already said, the talk would be about low energy states and CPT invariance at the Big Bang. Okay, so let's see if I can. Okay, so here you can see the abstract and the overview of the talk. So basically, the idea of the talk would be to study quantum field theory in a very special universe that would be a radiation-dominated universe, and we would do the analysis for scalars and spin one-half fields. So I will show you a bit about how to pick up correctly the vacuum state in this universe, how to make sure that the vacuum state is Hadamard, and then I would tell you something about phenomenology and about, I think one of the main or of the key points of the talk would be to tell you why we care about this simple model. And then I would try to relate the ideas to things that you are maybe more familiar with or that you know. So this is the overview. First, I will spend a lot of time or some time talking about motivation and the background, just to make sure that we are all in the same page. And again, to tell you why we care about this issue, which is like something that could have been done or has been done in a different way many years ago. And then I will tell you about the model, about quantum state in this CPT symmetric universe. And then we will talk about this Hadamard condition, the different vacuum choices that we have, and then some pheno that we can have. Then the third part of the talk would be about this method that, sorry, I didn't put it in the abstract, maybe I should have done that, would be about the method of states of low energy, which is a method that would allow us in cosmology to build, like in an algorithmic way, Hadamard states that have some physical meaning. And then finally, I would tell you a bit about the summary of the work, about some conclusions, and if I have time, I would tell you also about some extra or related comments that I think could be interesting. So first, when you invited me to give this talk, I was not very sure about the topic, but then after attending to the first talk of the seminar series, I thought this would be a right topic, because I think some of you care about a lot of you care about the early universe cosmology and about the conformal anomaly. So I think this would be kind of related to that. Oops, sorry. Okay, so we can start with motivation and background. And as I said, this section would be a bit longer than usual. And it would be, the idea of this section would be to try to give you some motivation and to share some ideas. And then I think you would understand why we care about the problem that we try to resolve or to understand. So first, this slide, I'm sure you are all familiar with this. It's about quantum field theory in curved spacetimes. Just to remind you, it's a semi-classical theory where we study the matter degrees of freedom propagating in a curved background. And then this gravitational background is classical. So we could do, this framework has different layers, but we would stay in the simpler one, in the pure quantum field theory in curved spacetimes, where the background is fixed, is given, and then we study the fields as test fields propagating in this background. Then a different layer of complexity would be to study semi-classical gravity, where we would study the back reaction problem, but we in this talk would stay in this first layer. And we learned a lot in the last century about quantum field theory in curved spacetimes, but what I want to highlight now, because it would be relevant for later, are these lessons that you can see in the screen. The first is that in general, in quantum field theory in curved spacetimes, particles are created due to this dynamical background that we can have. For example, in expanding universes, we would have in general quantum creation of particles, like scalar particles, fermions, spin one particles. This would happen like in general. There is one exception, which is when we have conformal invariance. In the case where we have for scalars massless particles and conformal coupling, scalar particles are not created. And then related to this first point, we have the second point that is that we would also have, in general, quantum creation of gravitons. So in cosmology, these tensor perturbations in an expanding universe are equivalent to study a pair of massless, minimally coupled, not conformal coupled, minimally coupled scalar fields. We can see this equation here. These equations are not conformal invariants, and then in general, we would have particle creation, creation of gravitons. But there is one exception, which is in the radiation-dominated case, because in this case, we are in the special case where R is equal to 0, and then this would make somewhat equivalent to have minimal coupling and conformal coupling, and then the creation of graviton vanishes. This is only in this special case when it happens. This is the first thing I wanted to tell you about particle creation. And the second point that I wanted to make is that it's also very important to know the UV structure of the theory, because as we know, the UV structure of the theory is much more complex in curved spacetimes compared to Minkowski. So then a lot of subtleties arise. For example, regarding renormalization, normal ordering is not enough. We need advanced techniques. And then it's important to make sure about the UV structure of the theory, both to have these appropriated renormalization techniques, but also to make sure that when we fix our initial conditions, when we fix our initial state in this Heisenberg picture, if you want, we end up with, we define the initial conditions properly so that we have finite results after renormalization. I'm sure you are familiar with that, but this would be the key points of the theory that would be relevant for later. So I thought it was important to remind this to you. And now let's talk a bit about the early universe. Oops, again, I don't know why. Okay, let's talk a bit about the early universe and about the some ideas and some motivation. So what do we know about the early universe? So observations tell us that soon after the Big Bang, the universe is homogeneous, isotropic, especially flat, and radiation dominated. And this initial state of the universe, if you want, is a bit strange. So why is so homogeneous? Why is so isotropic? Why is so spatially flat? So in general, the maybe most successful model or paradigm to explain this is the inflationary model, the inflationary paradigm, where we say that a period of inflation is required or happen to recover the observed simplicity that we see in the universe. Inflation not only provides this, but it also, through this cosmological perturbation theory, also provides a simple explanation for the scalar perturbations that we observe, like through the CMB, for example, and also as a consequence of the framework, which is quantum field theory in curved spacetime. It would also predict the creation of primordial gravitons. We would expect to have, as we have this scalar power spectrum, we would also expect to have or to observe soon this primordial power spectrum of tensor perturbations. And this is the framework that we know, and I think we are all very happy with. But now in this talk, I wanted to tell you about maybe another approach to the early universe, which is related to the Weyl curvature hypothesis. So the idea is that instead of saying that the initial state of the universe is strange, and then we would need an explanation to have it, we can say that maybe the initial state is somewhat expected or somewhat natural, and then we would need to understand what symmetry or what's happening behind to indeed get what we observe. But it's not that it's something strange, but it's something that is telling us some property about the early universe. So one idea that we can try to perform or to follow to understand this is to study the gravitational entropy. So we can say, we can build the gravitational entropy, and then we would see what's the state or what's the solution that gives us the lowest gravitational entropy state. And if we do this analysis, we would see that then the solution is the zero Weyl curvatures universe, and then this corresponds to Friedmann-Robertson-Walker universe. So then we can say that using this argument, then we would expect that this homogeneity and this isotropy. This is another way to understand the early universe. What does quantum field theory in curved spacetime to say about that? So I think in the 80s, Parker and Hu studied this issue, but then Hu wrote a very nice, Hu wrote a nice review that I suggest you to study or to see, which is that if we study, what they did was to study an anisotropic universe, and they saw that back reaction effects would dump away irregularities. So in some sense, quantum field theory in curved spacetimes or semi-classical gravity would help us to get this initial homogeneous and isotropic state. And in this case, in the case that we have a Friedman-Robertson-Walker universe, the Big Bang singularity becomes very special because then it's smooth and it can be reabsorbed in a conformal transformation. And furthermore, if we have, if we look at the observations and we assume that the initial state of the universe would be radiation domination, we then don't have creation of primordial gravitons, so we wouldn't observe these primordial gravitational waves because in this case this particle creation is forbidden by the emergent, if you want, conformal anomaly. So now with this explanation, I don't want to tell you, no, we shouldn't believe inflation and we should follow this. I just wanted to tell you this was the initial motivation to understand a different approach to cosmology, and then we wanted to see what would be the consequence of following this second approach. But I'm not saying that I would prefer the second compared to the first. I just wanted to study what would be the consequences. Okay, so if we want to now compare these two ideas from something that is very familiar to us, we would be, I think, very happy to look at the anomaly, to the conformal anomaly or to the conformal symmetry. So I think the inflationary paradigm or the inflationary theory can be understood very nicely through the conformal anomaly. As discussed in the first talk of this seminar series, quantum field theory in curved spacetime can produce an inflationary phase very easily and very nicely through the conformal anomaly. So there is a clear relation between conformal anomaly and Starobinsky inflation. And I really recommend you to read this paper. I even wrote the name, so you can Google it if you want. And that explains you the relation between Starobinsky inflation and the conformal anomaly. On the other hand, the second model I told you, the second mindset I told you, seems to be telling us that this conformal, that the universe, the early universe has a symmetry, has a conformal symmetry that should be emergent. It's not something that, it's something that appears. But then this is not compatible with the conformal anomaly. So there should be some kind of anomaly cancellation to allow us to follow this second approach. So we could ask ourselves how can it happen? So let's assume for now, for the second and third part of the talk, that we don't know how, but this anomaly cancellation happened, and then we can still have conformal symmetry or this emergent conformal symmetry in the early universe. Let's assume this for now. At the end of the talk, if I have time, I will tell you which mechanism we can have that cancels the anomaly. But for now, let's assume that we have anomaly cancellation and see what are the consequences of having as an initial state for our universe this radiation-dominated Friedman-Robertson-Walker homogeneous isotropic universe. Okay, but I don't know if I. Okay, let's do this. Okay, so let's do that. Now I almost finished the motivation section, and I will show you the computations. But this was the motivation for which we started studying this problem. So now let's go to the main technical points of the talks. As I told you before, the rest of the talk, or part of the rest of the talk, would be about studying quantum states in this CPT symmetric universe. Okay, so let's assume that the initial state of the universe, or the natural state of the universe at early times, was this hot radiation-dominated era that can be described in conformal time by this metric that you see in number 2. And we see that this metric is invariant under tau going to minus tau. So this conformal time, the metric is invariant under this change of sign. So then we can use this property of the metric to study the quantum field theory with this symmetry in the early universe. And this is the idea that follow Boyle, Finn, and Turok in 2018, where they propose this CPT symmetric universe. They publish a series of papers starting from this one, where they try to propose this new cosmological model that doesn't need inflation and tries to explain the early universe cosmology using different arguments. So the starting point of their work was this CPT symmetry, and was to see how quantum field theory behaves in this context. So we follow what they did, and then we wanted to see what quantum field theory in curved spacetimes from the technical point of view has to say about this idea that they are following now. It's something that is, this model that they are following is still under construction. So every, let's say, year they publish something new. So if you are interested in those ideas, I would also suggest you to follow what they are publishing. Okay, so what they were saying is that it's natural, given this symmetry too, that the early universe, the state of the universe, should also respect this CPT symmetry, which includes the space-time and the quantum state of the quantum field theory on that space-time. So C and P are naturally satisfied in Friedman, Robertson, Walker, and the key ingredient is now T. So now to do the analysis, we would focus in scalar fields. So we would consider a scalar field and do a standard Fourier transform to study this vacuum state. Okay, let's go to the second part, quantum states in CPT symmetric universe. Now the idea would be to study the equation of motion for the field, to solve the equation, see which are the degrees of freedoms, and try to understand these initial states near or close to the Big Bang to have some physical intuition about them. So for simplicity, instead of working with the field, we would work with the Weil's rescale field that is like that. And then if we compute in this framework the equations of motion, we would have this equation for the modes. This gamma, I would work with rescale variables, so the gamma would be related to the mass, and this kappa would be related to k squared, okay? Now, if we can solve the solutions using the equations using Mathematica, and then we would easily arrive to 5. So again, it's a second order differential equations. We have 2 linearly independent solutions, and then we have 2 constants to determine. So usually when we do quantum field theory in curved spacetimes and we have to do these kind of computations, we usually put one solution here and the complex conjugate here. But we decided to work in a different basis because it was easier for us. So it means that C1 and C2 are not Bogoliubov coefficients. They satisfy other, if you want, normalization conditions, but this is completely fine because those two are linearly independent. So the solutions can be written in terms of parabolic cylinder functions, as you can see here. Now, as we said, if the background has one symmetry, the field has to, the field also has to satisfy this symmetry, and this time reversal symmetry implies the following condition for the modes. So imposing this condition in 5, we would get this constraint for the constant C1 and C2, and then we would also have the normalization condition, so we would reduce 1 more degree of freedom. So basically, we started from 4 degrees of freedom. We have C1 and C2 real and complex. Then this time reversal symmetry reduces from 4 to 2, and the normalization reduced to 1. So we know that now fixing like 1, for example, let's say the real part of C1, we would fix our solution. So we only have 1 degree of freedom. Yes, so now we can do this, and then we know that we would be able to label all the different solutions, but this is not very illuminating. It's like, okay, yes, we have less degrees of freedom, and then what? So now what we wanted to do is to study the solution of these equations close to tau equals 0 to see how would they look like. So let's take us now a look to the mode equations, and around t equals 0, we see that the mass of the field becomes irrelevant. We have, because yes, everything behaves like radiation. And then the solution of this equation can be written as a linear combination of positive and negative frequency solutions, the ones that we use in general in Minkowski. And then if we also impose time reversal symmetry and normalization, we would end up with a solution that would have to look like that. This is how the solution of 9 looks like. And then if we study the solution at tau equals 0, we would see that we have this 11. So what we can do now is what we see now is that we can fix our solution by fixing this theta trigonometric angle that we have introduced in TEM. So the idea is now that fixing C1 by hand would be something very not very clear. But now with this, we have a clear picture of what the initial conditions would look like, because fixing the angle would fix C1 and C2 and everything. And then we would see that depending on the initial angle for the field, we would have one solution of or another. So we would picture in our heads better why we should choose one initial condition with respect to the other. Yes, what I said here, the CPT requirement reduces the space of possible vacuum states to a family of states characterized by the hyperbolic initial angle, theta. Now, in terms of this parameter, we can write the constant C1 and C2, and it looks a bit complex, but actually we don't care, because we only care about the physical meaning that maybe the angle can have, which is this one, and then we would put the things in Mathematica and we would compute. Again, as I said, any choice of theta would correspond to a different choice of the initial vacuum. Now, not all possible solutions in a radiation-dominated universe are CPT invariant, because we reduce all the possible solutions to this one parameter family. There are other solutions that are maybe not the natural choices or the natural solutions at late or early times that do not fit into this category. For example, if we take tau going to minus infinity or plus infinity, the expansion of the universe becomes adiabatic, h tends to 0, and then we would recover the Minkowski-like solutions for our equations. And then from this, we can define the plus and minus vacuum, but they are not invariant. They are actually, one is a CPT of the other. So here you see, so we take the general solution, we go to minus infinity, and we would see positive frequency solutions, negative frequency solutions, and we would say that the natural choice is this one. And again, same for the plus. Now, what can we do once we have our initial states? So we can study particle number, we can study the particle creation. This is the easiest thing we can do. Particles are defined at in the far future as excitations of the out vacuum, which would be the natural vacuum at late times. And then what we would do is to compute this in-out amplitude if you want. And then we would see for each choice of the, initial condition or for the initial vacuum, what would be the particle number at late time. This is again, standard computations in quantum field theory. We can write it in terms of this hyperbolic angle, and we get this expression here, particle numbers at late times as a function of the initial condition, theta. Now, although maybe it's not clear in this expression, there is one choice that minimizes this particle number, which is this quantity that you see here in 13. This is the angle that minimizes the particle number at late times. And this is the choice that Boyle, Finn, and Turok made in their original article, where they wanted where they presented this model. They claim in the article that this was the only choice and that this was somewhat analogous to the Vance-Davis vacuum, but this is not true, because in this case, we would have this K dependence, so we would have more possibilities, as you would see later. Okay, so now how do we choose theta? Because like here, I show you that the possibility to choose theta would be to say, okay, let's minimize this number and see what we obtain. What else can we do? We can use physical arguments. Again, the first option I show you, the Boyle, Finn, Turok option, would be to say that the vacuum state is the state that produces the minimum amount of particles at late time, this choice of the theta angle. And then if we study the scaling of the particle number for large scale, we would see the scaling. Another choice could be, we saw that at early times, the mass is irrelevant. So it seems that there is some emergent conformal symmetry, because yes, all the fields, because R equals 0 makes the conformal and minimal to be kind of equivalent. Okay, then we could say that we should choose the state that seems to be preferred by the emergent conformal symmetry, which would be theta equals 0, saying the standard choice for a particle that we would do in Minkowski. And if we make this choice and we study the scaling of the particle number, we would see this K to the -4 scaling. So different choices would give us different predictions or different phenomenology. Now, here I show you the result for scalars, or the computations for scalars, because it was easier or simpler. But for fermions, you can do the same. You can do the same analysis, and then you can also find trigonometric angles in this case. And in this model that they studied, so they not only say, no, the initial state of the universe should be radiation dominated, but they also try to explain many things. For example, this anomaly cancellation, they try to explain dark matter. And then they say that in the context of this CPT symmetric universe, there is a natural candidate for dark matter, which is a very heavy right-handed neutrino, which is decoupled from all other particles of the standard model, and then it would be only produced gravitationally. So then the idea in the following slides would be to show you that different choices of theta would change the prediction for this neutrino. So here, what I'm showing you is the particle number, or beta, for two different choices of the initial angle. So in purple, you see this choice that minimizes the particle number. And then in blue, you would see the theta angle equals 0. And then you see that more particles are produced. And then if from this result, we try to compute the mass of the dark matter particle following some standard computations, we would see that the prediction is different. We would see that in one case, we have this 4.8 here. And in the other case, we have 1.6. Okay, but we would still have the same order of magnitude. So we see that the choice of the initial condition or the choice of the initial state is relevant because it gives this solution is 3 times this other solution, but okay, still is the same order of magnitude. So I guess it's up to you to tell me if you think this is a lot of range or is a short range, but actually there is a difference. So choosing different theta, we would have different phenomenology. So it's important to make sure that the initial state is chosen in a way that makes sense. Now, maybe some of you are already thinking about what I'm going to say now, but are all these choices or all these states possible? Are all these CPT-invariant backwards acceptable? The answer is no. So here I cited one article by Professor Fulling, which was not exactly saying what I'm saying now, but okay, it was very similar. So basically in this article is shown that Hamiltonian diagonalization doesn't work always to give us good initial states for our theory. So basically, maybe you would understand this statement better later, but basically the answer to this question, are all the CPT invariant backward acceptable? The answer is no. It's not because we have to impose an extra condition, which is the Hadamard condition, the ultraviolet condition, the adiabatic condition. That basically means that our state has to be adiabatic at any order. And this is necessary to make sure that our observables are finite in perturbation theory at any order. For example, if we study the stress energy tensor, we can study the renormalized stress energy tensor with the subtraction here. So only if we choose the right value of theta, we would have that this quantity is finite after renormalization or after regularization, after subtractions. And this cannot be, this should be done at any order, because we can, if we cut the adiabatic expansion, then we would have something that is finite, for example, for the stress energy tensor. But then if we compute T mu nu contracted with T rho sigma, we would have something divergent. So we have to make sure that this is the ultraviolet condition, the Hadamard condition, is imposed at any order. So now, the thing that we did in our paper is to study which states or which initial conditions satisfy this adiabatic condition, and we realized that it was not all of them. It was not this big family that I showed you before, but only a subset in this family, which are the states for which the associated initial angle at k going to infinity satisfies this asymptotic expansion. This asymptotic expansion, which is like infinite, okay? So I put here dots, but actually it's like you have to check, or you have to see that this is satisfied at any order. This condition is an asymptotic condition, so then it doesn't fix univocally the vacuum state. It's an asymptotic condition, so then there are still many vacuum states that satisfy this condition. So now, if we go again to the two states that we consider, the one that was preferred by this emergent conformal symmetry and the one that minimizes the particle number, we see that the choice number 1 in this case, the choice that minimizes the particle number, satisfies the asymptotic condition, is an adiabatic state, but the choice theta going equals 0 does not satisfy the condition, okay? You see the expansion, 0, of course, doesn't satisfy this expansion. So it's not a valid choice. So the idea is like, okay, this is not valid, but then is there any suggestion? How can we build other states that make sense physically and then satisfy this condition? So another way to ask, is there any algorithm that generates adiabatic states so we can easily analyze and understand them? And the answer is yes. So it's now what I'm going to do is to explain you what's the algorithm and how does it work. So this algorithm was introduced by Olbermann in 2007, and I think for many years it was not very popular. So the article has not many citations, but in these last recent years, I can see that the article is getting cited again, and I think it's a nice, let's say, algorithm or a nice idea. So I'm quite happy to explain this to you. So the idea is that he proved that for scalars at least, minimizing the smeared energy density of the field modes gave us adiabatic vacuum states. The smeared energy density is defined like this. So we have here the standard energy density. Here we have a window function. And then here we have this time average. So the idea is that if we minimize this quantity here, we would have, or we were, in the way I will explain you later, we would have adiabatic states. And then we would, but then we would have a new degree of freedom, which would be the choice of the window function. But maybe choosing the window function in the where we want would give us, again, some control in the choices we are making. Okay, so now in this part 3, I will tell you a bit how this algorithm works. I would tell you about the states of low energy. Okay, so the procedure is quite, I think it's clear. So it's very, as I said, algorithmic. So it works as follows. So first we have to define the smeared energy density. Here for simplicity with the equations, I choose the minimal coupling. So then we have here the window function, and then we have the time average here, and then we have here the energy density, that this omega is k squared plus m squared a squared. Remember, we are in conformal time. And then here for the smeared energy density, we have to define it with respect to the original field, not with respect to the value scale rescale field. This is step number 1. Then the 2 is that we choose we expand the field modes in a basis of solutions, B and B star. So for example, in this case where we want to impose CPT, what we can do is do this, the most natural choice would be this expansion. So would be to use the fact that we know the properties of the solution, and we work with the initial angle to define 23 as follows. So this hyperbolic cosine multiplied by B, and this hyperbolic sine multiplied by B star. And here B is the solution which at tau equals 0 corresponds to this positive frequency solution that we have at tau equals 0. And then imposing time reversal is why we get cos and sine and not some random functions. This is step number 2. Step number 3 is to minimize this smeared energy density as a function of the 3 parameters, in this case, the theta. So then we do this computation, and then we would isolate for theta, and we would get this result that you see here in 24, where here C1 and C2 are these quantities that depend on the basis B. So this is like the energy density for the B modes, and then this would be a related quantity. And we can see that actually the result depends on the window function. However, although it's not clear from this prescription, this is independent of the basis, because independently of the basis, we would have a combination that would give us the same theta for a given f. Okay, so this is only a choice that is a preferred or is natural in this context, but we could do the same construction for a different basis and obtaining the same state. So now the nice thing of this algorithm is that it gives automatically adiabatic states, and it was proven by 4 scalars. Now, in this previous slide, I show you how this works for when we impose CPT, and you can see it because here the 3 parameters are Okay, the free parameter is this theta. But we can do this prescription in general. If we do not impose CPT, we can see, or we can, after doing the construction, we can see that for any window function with compact support at tau going to minus infinity, we would recover the adiabatic vacuum. So this natural vacuum that I said that we would have, this Minkowski-like vacuum that we would have minus infinity. Now, for any window function with compact support at plus infinity, we would recover the late time adiabatic vacuum that we call plus. Now, if we impose CPT for any window function with compact support at plus and minus infinity, making sure, okay, that we have CPT, then we would recover this Boyle-Finn-Turok vacuum, this vacuum that this choice that minimizes the particle number at late times, which is the one that we see in 26. But the good thing with this algorithm is that now we can also study what happens around tau equals 0 if we minimize the smeared energy density at the Big Bang. So what will happen here? So here is not that nice or that easy as it was in minus infinity plus infinity or this in this CPT case, because the result depends on the window function. So different window functions would give us different theta. And in general, we wouldn't have analytical solutions, but we would have something that we would have to compute numerically. Because if you go here, you see that these integrals in general wouldn't be, cannot be computed analytically. Now, this choice in general, okay, I guess it would depend a bit on the window function, but is close, is phenomenologically close to the naive choice, theta equals 0. So one can argue that even though this choice is not valid, it would be a good approximation if we want to do some quick phenomenology and we only care about two-point function or maybe about stress energy tensor. The other subtlety that we have in tau equals 0 is that tau equals 0 is a very special point if you want, and it's not always possible to find a valid result for all k, because we would have it for yes. So it's a bit involved. Maybe I don't have the computations here, but basically not all window functions would give us a choice that we can use, and that is adiabatic. So we have to be careful. So in particular, I think I didn't write it here, but one condition that we found is that f squared over tau squared should be finite. So not all window function, we cannot use any window function. We have some restrictions. Otherwise, we will find that a state that wouldn't be adiabatic, even if we follow the prescription. So this is a subtlety that we have to take into account in this case. And then for the fourth point that I wanted to make is that for massless and conformally coupled fields, in this case, theta equals 0 is a valid choice. It's the preferred choice when we choose a window function with compact support at tau equals 0, and this is independent of f. So so if you see this expansion, you see that this is related to the mass. So for mass equals 0, all these terms vanish. But this is something true for conformal coupling, not for minimal coupling, because the low energy states work with the stress energy tensor, and for the stress energy tensor, being in minimal coupling or being in conformal coupling is relevant. So this is my argument that I told you before, where we said that minimal coupling and conformal coupling were kind of equivalent is not that true, if you want. Now, we repeated the analysis for fermions, and for fermions, yes, the same analysis can be done. I didn't give you here the results because I thought it was maybe complex, but actually maybe this is one of the main results of the paper, because in the paper what we did is we built these states of low energy prescription for fermions, both in general Friedman-Robertson-Walker and for CPT. And I think it's the first time that it was done, but we didn't prove that these low energy states were adiabatic. We show strong evidence, but we didn't have the proof. So maybe if some of you is interested, it's a good research direction could be to do formally the proof, because we only give some hints and show the procedure, but we didn't prove it. So again, for fermions, it's very similar to scalars. We can build these CPT symmetric invariant states. And in this case, as in the scalar case, the CPT requirement reduces the space of possible vacuum states to one parameter family of solutions that can be parameterized now with a trigonometric angle. So before it was hyperbolic. Now it's trigonometric and we call it theta. This is related to the picture I showed you before. Again, not all these states are compatible with the Hadamard or with the adiabatic condition. And again, we can repeat the same analysis and see which states would be compatible with this Hadamard condition or with this infinite order adiabatic expansion. And then we found the requirement, which is what you see in 27. So again, not all solutions, not all angles are valid, but only the ones that satisfy this expansion for large K. Again, what I said you before, the states of low energy prescription can also be for fermions. We did it for Freeman, Robertson, Walker, and then for CPT. And for CPT, we find this solution where C2 and C1 now are, of course, different to the ones I showed you before, but they are quantities that are related to the basis of solutions that we choose for our problem, even if the result is independent of the base. It depends on the smearing function. And then again, it's very similar to scalars. So if we are at late times, at early times, and we forget about CPT, we would have that the adiabatic vacuum is the preferred one. If we force to CPT, we would find, and then we have a smearing function with compact support at plus and minus infinity, we would find that the preferred solution is the state that minimizes the particle number. And then if we want to do the same analysis, but choosing a window function with support at t equals 0, what we would see is that in general, the choice is not unique. It depends on the smearing function. Again, we have some restrictions in the window function because otherwise we would have problems and the states that we would obtain wouldn't be adiabatic. And then again, there is this special case, which is the massless case, where in this case we have conformal symmetry, where we would find that the preferred solution is the conformal vacuum independently of the smearing function, as we would have expected. Okay. So, okay, I think I will, now that I see the clock, I think I will finish earlier, but okay, I think that's not too bad. So now I'm going to part 4. I'm going to tell you about summary, conclusions, and some extra comments. Okay, summary of the talk or of the article, I think is quite clear. What we did is to parameterize the CPT-invariant vacuum states in radiation-dominated universe, paying attention at tau equals 0, because we wanted to understand what was happening there, in terms of one real phase, theta, or capital theta for fermions. In this case, it was hyperbolic. In this other case, it was trigonometric. Then we study the UV properties of these states, and we found that not all the CPT-invariant vacua are admissible. So we have to impose this adiabatic condition, this Hadamard condition, this UV regularity condition. However, this condition, unlike what happens in the sitter, this condition doesn't fix uniquely the vacuum state, but gives us some asymptotic condition, but there are still like infinitely many possibilities. Actually, although I tell you more about the model and about some concepts, the article mainly focused in this algorithm of state of low energy that generates adiabatic states. But some cases we have to be careful with if we want something with support at tau equals 0, we have to be careful with the window function. But this can be done, and we can obtain adiabatic states using this smearing function around tau equals 0. And then I wanted to make some comments regarding the sitter, comparing the sitter with this radiation-dominated universe, because the construction is very similar. Yes, I think it's very similar. In the sitter, we can also study quantum field theory in the sitter. Then we can impose the symmetries of the background, and then we would have a one-parameter family of solutions of acceptable vacuum choices, which are usually called the alpha vacua. And then there is one difference. So if you remember, in this case that we are studying in this radiation domination, this one-parameter family depends on K. But here, because in the sitter, the sitter is very special, and we have this kind of UV-IR relationship, actually the consequence of this is that this alpha is a constant that doesn't depend on K. Now, if we go to the sitter and we study UV regularity, we would find that not only alpha and aqua are ultraviolet regular, but only the Banks-Davis vacuum, which is characterized by alpha equals 0. In this case, UV regularity would fix only the UV, but then because of this thing that the sitter has, fixing the UV would fix the IR. So then we would fix the full state for all K. Instead, in this CPT symmetric universe, we would have still many choices, even if we fix the UV. So it's not exactly the same. The sitter has more power in this sense than radiation domination. So it's not the same. And we would still have many vacuum choices that are UV regular instead of one. So this is what we did. And now, since I see that we have time, I would tell you a bit about this anomaly cancellation. So before, I was telling you that we could understand maybe these two different ways of understanding the early universe through the anomaly. And I was telling you that in quantum field theory in curved spacetime, it was very natural to explain inflation through the conformal anomaly. In particular, I told you about this paper that, okay, this Starobinsky, that the Starobinsky model can be obtained through the conformal anomaly. And then instead, if we wanted to maybe say that instead we had this other radiation dominated model, we would have to find a way to remove the anomaly to make this analysis consistent. So the initial argument of these maybe ideas was that the Big Bang singularity is very special, it's smooth, and can be reabsorbed in a conformal transformation. But I was telling you this is not possible if we have the conformal anomaly, because the initial singularity then cannot be fully absorbed by a local conformal transformation. The conformal anomaly, like very schematically, looks like that. It's independent of the quantum state, and then this coefficient C and A would depend on the particle content of the theory, depending on the number of scalars that we have, number of fermions, number of spin 1 fields. We would have like different numbers here. So then, although I'm writing here, okay, you are seeing everything, but although I'm saying here that the possible cancellation would be a possible solution would be anomaly cancellation. This is not possible in the standard model because all the particles contribute in the same way, so there couldn't be. But one smart idea that these authors has was that they realized that there are some fields, which are these new fields called dimension zero scalar fields, that contribute negatively to the anomaly. So they have negative values of A and C. And what they saw is that there is a fixed number of these fields, actually 36 fields, that exactly cancels the anomaly. If we consider all standard model particles, including 3 right-handed neutrinos and excluding the Higgs boson, that would be then a composite particle or something like that. So although this number seems a bit big, okay, I understand, but it's not guaranteed that there would be a solution of this equation. So the fact that there is one solution is quite nice. And then, yes, you can see that this idea is a bit, this is maybe not ideal because, okay, if the price to not have inflation is to include in my theory 36 fields, I don't gain anything in complexity or simplicity. I still have something which sounds very complex. But actually, there is one thing that these, well, there are many things that these dimension zero scalar fields have. So one thing is that they are the only physical state that they have is the ground state. They cannot produce, particles cannot be produced. And then this means that they wouldn't they wouldn't change much phenomenology. They would never be detected. They are only there to kind of solve our problems, if you want, because the only, sorry, as I said, the only vacuum, the only state that they have is the vacuum state. And then another nice property of these dimension zero scalar fields is that they have a scale invariant power spectrum. In general, Friedman, Robertson, Walker. We don't need to put the sitter to reproduce this scale invariant power spectrum that we have in the sitter. So this would be true for any Friedman, Robertson, Walker, which is also a nice property of the yes of inflation. Okay, so I think with this, so when I was practicing and preparing the talk, it was longer than 1 hour, but here I was quick and it was that's it. So I'm done. So thanks for listening to me, and I would be happy to answer questions.
Thank you very much, Silvia. A nice talk. Yes, I would like to open it up to the audience to see if there are questions. Please raise your hand. I see a question from Jean-Alexandre. I hope I'm pronouncing that correctly.
Yes, thank you. It's a bit a naive question. Could this window function depend on the K?
So I think maybe, I don't know. In principle, I would say no.
I mean,
but
would there be any advantage, or it doesn't make sense, or maybe some assumption forbids this dependence?
Yes, so I think that this is a good point. I don't know. Maybe some people in the audience know. In general, I think it doesn't depend on K, but actually here, yes. So in point 3, here I said it's not always possible to find a valid result for all K, but it's possible to find it for some K. So maybe if you find a K-dependent window function, it would solve the problem. Maybe.
Yes.
I think in general, so yes. Again, I'm not. I usually don't work with these smeared functions, but actually, I think usually they don't do that. But I cannot tell you why yes or why not.
Okay, thank you.
Any further questions? Otherwise, I have a question about this final slide about these dimension 0 fields.
Yes.
So you said something like, they only have a ground state, which is also something I've heard Neil Turek say. But in curved spacetime, this is a bit confusing because you can ask a ground state to what? Now, of course, I guess in FLRW, you can think, okay, maybe you mean something like a conformal vacuum or something like that. But do you have any idea what this would mean in some arbitrary curved background? What states of this field would look like?
No, I don't know. I don't know. I just, so I think the only thing I know of this issue is what I put in this slide. So I don't know. But I think it's a good question.
Okay, thank you. Any further questions? Sebastian.
Yes, Silvia, sorry. I would ask you also about this slide. I don't understand really, when you say that the initial singularity cannot be fully absolved for T-minimum because of the anomaly, what do you mean?
So if you do a conformal transformation and you work in the conformal space, if you have the conformal anomaly, you would have a part of T mu nu so it wouldn't work because you would still have some part of this new T mu nu that would have something singular there. So I think. So I should maybe before I had a longer slide, but basically, so if you do a conformal transformation, then the resulting the conformal theory would be like Minkowski, and then you wouldn't have any problem. And in principle, you wouldn't have anything that goes as 1 over t squared or something like that. But because of this conformal anomaly, I think it's not the case. Even if you do a conformal transformation of the stress energy tensor, you would still have some 1 over tau singularities, even if you multiply your stress energy tensor by a to the 4, something like that. I don't have the computations explicitly with me, but I think this is what it means.
Okay, that's fine. Thanks, Silvia.
Any further questions? If not, perhaps we could.
Sorry, may I have a question for Silvia, if I may? Hi, Silvia. Thanks for the talk, and sorry for the delay. By the way, I had a bureaucratic emergency here in Trento, and I was late. Many sorry. About the comment on Olbermann states, if I understood correctly, the construction is similar to original Olbermann states for Friedman and I mean adiabatic states, and I think that the smearing is over the time because you essentially take advantage of spatial translational invariance of states and so And so you can essentially solve the mode equation in terms of the spatial direction in Fourier. So what it remains is that the energy density depends of time as well as the modes. So when you take the smearing, essentially the test function, the compactly supported test function must be supported only over time, because you need to regularize your density only over the time. If I remember correctly, the construction by Olbermann. So
yes.
Okay, great. This was the first comment. Instead, I have a question about the trace anomaly cancellation you mentioned at the end. I don't know that that paper about the introduction of this zero mode, these zero scalar field terms, let's say. But I have a question about the appearance of the trace anomaly. When you compute the trace anomaly, you have terms such as box R, for instance. If you the presence of the trace anomaly might spoil a bit the form of the stress energy tensor due to this kind of stuff of time on higher order terms, let's say. So I was wondering if how this field may cancel all this problem, that in the sense that you can reabsorb, if I understood correctly, the all these contributions in your trace.
So yeah, I think it's a good point, and I think yes, this expression in 29, I copied this from the paper. In this paper, I think they only give this C and A coefficients, but in general, I think that we can also have this box R coefficient and everything. I don't remember why they don't put it, but I think they have a reason. I just forgot.
Okay, no problem. No, because for instance, in cosmology, in Friedmann equations, in the semi-classical case, usually box R is dropped by choosing a suitable renormalization constant, for instance. So maybe you have other criteria to avoid them. I was wondering if the introduction of this scalar field may, I mean, let's say, gather all these choices in the sense that choosing this scalar field corresponds to, for instance, to choosing the box R normalization constant, something like that. So.
Okay, no, then I think no, because let's assume that box R can be removed during this choice.
Okay.
Then what they do is like,
I see.
yes. Then the thing is that, for example, let's say for scalars, C would be 1, for fermions would be 2, for spin 1 would be 3, and then for these guys would be -1/2. And then they did some not number theory, but they solved these algebraic equations and see if they could find some integers, and then they found that there is a solution, which is
there is a solution.
36.
I see. Okay, many thanks.
Okay. If there are no further questions sort of on the recording, I suggest we stop recording.
Okay, I'll stop it now.